The aim of this lesson is to outline the inextricable links between magnetism and electricity. The fundamental aspect of the link between electricity and magnetism is that any flow of electric charge will create a magnetic field. We will now investigate this phenomenon, explaining how the magnetic field may be predicted and put to practical use. In 1820, a Dane named Hans Christian Ørsted observed that a compass needle was deflected away from its north-south alignment when placed near a wire through which a current was flowing. He saw that the compass needle aligned itself at right angles to the wire. When the current was switched off, the compass needle returned to its north-south alignment. Ørsted's experiment revealed that there is a magnetic field around a wire which has a current flowing through it. But this magnetic field has no beginning and no end. This magnetic field has no discernible north or south pole. Further experiments show that the magnetic field around a current-carrying wire is always at right angles to the flow of current, and can be described as being in the form of concentric circles. That is, circles which are of different sizes, but which share the same center. The magnetic field lines always point in a specific direction around the wire, either clockwise or counterclockwise, depending on the direction of the current flow in the wire. A good technique to predict the direction of the magnetic field around a wire is to point the thumb of your right hand along the wire in the direction of the conventional flow of current. Remember, that is the opposite direction to the electron flow. The direction in which your fingers now naturally curl around the wire is the direction of the magnetic field. Because of the similarity between this method of determining the direction of the magnetic field and the direction a right-handed corkscrew needs to be turned to screw it in, the method is called the corkscrew rule. In order to put the magnetic field around a current-carrying wire to practical use, we need to somehow convert the field into something similar to that produced by a bar magnet with a north and south pole. If we look in cross-section at two insulated current-carrying wires placed close together, with the current flowing in the same directions, their magnetic fields will combine, as shown here. If, however, we place two insulated current-carrying wires together with the current flowing in opposite directions, their fields will now interact like this. If we combine both of these effects over a number of wires, we will produce a magnetic field very similar to that produced by a bar magnet. This can be done very effectively by forming an insulated wire into a coil. The two ends of the coil will act as magnetic north and south poles. This device is known as an electromagnet or solenoid. In order to ascertain which end of the solenoid is the north pole, the right-hand grasp rule can be used. If you imagine holding the cylinder in your right hand, with your fingers curling around it in the direction of the conventional current flow, your outstretched thumb will be pointing towards the north pole of the solenoid. There are a number of factors which affect the strength of the magnetic field produced by a solenoid. We have already seen that magnetism is induced in a magnetically soft iron bar if the iron bar is placed within the magnetic field of a permanent magnet. The magnetic field of a solenoid will also induce magnetism in an iron bar. The electromagnet will be especially strong if the iron bar is placed where the magnetic field of the solenoid is strongest, that is, in the centre of the coil. Here, the iron bar is the core of the coil, forming a very effective electromagnet which will act exactly the same as a bar magnet. However, the electromagnet can be turned on and off at the flick of a switch. When the current is switched off, the temporarily induced magnetism in the soft iron core quickly dissipates, and it stops acting as a magnet. Try turning the current of this electromagnet on and off to see what effect this action has on the micromagnets in the iron core. The strength of a magnetic field produced by a coil is directly proportional to the strength of the current flowing through it. This graph represents visually the connection between the two variables, that is, the current flowing in an electromagnet and the strength of the field produced. As you can see, if the current flow is doubled, then the strength of the magnetic field is also doubled. Another way of increasing the strength of the magnetic field surrounding an electromagnet is by increasing the number of turns making up the solenoid. At a constant current supply, the strength of a magnetic field is directly proportional to the number of turns of wire in the coil which is producing the magnetic field. In aircraft electrical systems, the electromagnet is put to practical use in electrical relays. A relay is simply a remotely operated electromagnetic switch. It consists of a coil with a great number of turns of insulated wire, wrapped around a fixed core of soft iron. In this way, a large magnetic force can be created with a relatively small current flow. A soft metal armature is attached to a pair of electrical contacts, which, in our example here, are spring-loaded to the open position. But when current is passed through the coil, the soft metal armature will be attracted to the core and the contacts will close. When the current to the coil is switched off, the contacts will open again. There is no electrical connection between the control circuit and the circuit being controlled. The contacts of the relay can be used to control high current devices, allowing these devices to be controlled from a small remote switch, thereby reducing the amount of heavy expensive wiring required. Although any electromagnet can be referred to as a solenoid, the term solenoid has a particular meaning in aviation. In aviation, solenoids are used to open and close electrical contacts in a similar way to a relay, or they may be used to open and close valves in the aircraft hydraulic or fuel systems. The primary difference between a relay and a solenoid is that in a relay the soft iron core is fixed, while in a solenoid the core can slide in and out of the coil. With the solenoid de-energized, the core will be pushed out of the coil by the spring. When a current passes through the core will be attracted into the center of the coil, closing the contacts. You will recall that the lines of flux between two opposite magnetic poles look like this, and that the magnetic field around a current-carrying conductor looks like this. If the current-carrying conductor is placed between the two opposite magnetic poles, the two sets of magnetic fields will interact. In the area where the fields are running in the same direction, there will be a strengthened magnetic field. And in the area where the fields oppose each other, the field strength will be reduced. This will produce a force trying to move the conductor in the direction of the weakened field. In physics, this force is known as the Lorentz force. The Lorentz force is felt by all charged particles in an electromagnetic field. It acts at 90 degrees, both to the direction of movement of the particles and to the magnetic field. This is the basic principle on which electric motors operate. Here is a summary of the important teaching points which have been made in this lesson. Any flow of electric charge will produce a magnetic field. The magnetic field around a wire carrying an electric current takes the form of concentric circles, all centered on the wire. The direction of the field around a wire can be predicted using the corkscrew rule. The magnetic field produced by a coil is similar to that of a bar magnet. The north pole of the coil can be found using the right-hand grasp rule. The strength of a coil's magnetic field can be increased by adding a soft iron core, by increasing the current flowing in it, and by increasing the number of turns on the coil. A relay is a remotely operated electromagnetic switch with a fixed core, and a solenoid is a remotely operated electromagnetic switch with a moving core. If a current-carrying conductor is placed between two opposite magnetic poles, a force will be produced which will try to move the conductor.